So because we are going to learn today about this hardware, so I listed some chapter goals. Firstly, we are going to read an ads in this today's class, maybe later, and so that we can need to know what's the hardware or how we can understand such a kind of jargon of this computer. And then I also listed some computer components and what's their functionalities and how we construct a volume architecture in this volume machine, which is very, very important concept in this computing system or computer science. This is a human being, okay, who created today's architecture. And all the computers we use today, almost, we use the volume architecture. So he is a very important person in the computing system or computer science. How do you say, revolution, yeah. So, and I also will describe in this volume architecture or in this volume machine, how does the computer work? About the instructions. So one thing important is we use some kind of cycle, which we call it fetch, decode, and execute cycle to do all the jobs defined in the computer. When you do the programming, you tell the computer what to do. So this programming need a lot of instructions to execute. So in the computer, through the hardware viewpoint, it always need to fetch an instruction and decode the instruction. What does this instruction represent? And then it do the execution, and then to fetch the next instruction and do this cycle in the computer. So we are going to describe this in today's class. We also getting to know about the memory, okay, the memory, and we are talking about other storage devices, okay. So about this several items. That's the most important thing in today's class. So also in the hardware. So firstly, in fact, I'd like to talk about this ALU. So do you know ALU, and it represents, the A is arithmetic, L is the logic, so U is the unit. So it represents arithmetic and the logic unit. It means this unit can do the arithmetic operation and also the logic operation, okay? So arithmetic operation represents like adding or subtraction or multiplication or the division, okay, such kind of arithmetic operations. So logic represents some logic operations like and, or not, or a lot of such kind. That is, for example, we have cell to represent and. So that means the input, if the input is 0, 0, the output is supposed to be 0. It is 0, 1, it is 0. It is 1, 0, it is also 0. It is 1, 1, it is 1. Okay, so that is the AND, the logic operation, okay? Only both input is true. The output is supposed to be true. So it's some logic operation. So this ALU can do both arithmetic and the logic. Okay, so I showed here a chip, which is an ALU. It is one of the most famous chip, ALU chip. It is created by the Intel company, and its name is 74181. It's the first ALU chip, very formal ALU chip, so it's very famous one, the most famous ALU ever. So in the most modern ALUs, in fact, we use a lot of small spatial storage units. We call them registers. Okay. So later we are going to know more about the registers. So this is just one thing you need to know in this ALU. So firstly, when we talk about these ALU, we do the arithmetic, right? So when we do this arithmetic, one most important arithmetic is to do the addition, right? In the former, how the data are presented, we say that in the computer we do the arithmetic. When we do the subtraction, we can consider it as an addition, right? For example, 3 minus 2, we can consider it as 3 plus minus 2. So it's still an addition. So also for the multiplication, we can convert it to addition, right? 2 times 4 is supposed to be 2 plus 2 plus 2. So the addition is the fundamental operation for all these arithmetic operations, right? So firstly, we are going to learn how does this addition implement in this ALU. And in fact, we do not directly do this addition, or how can we say? In fact, when we talk about how when we do these arithmetic binary as arithmetic practices, we have carrier for the addition, and we have borrower for the subtraction. Do you remember the concept? So in the computer, we need to consider firstly the addition directly, and second one, the addition with this carrier. So here we firstly, to learn about the first concept, is a half adder, we call it. So it is plus A and B, and you obtain a result sum. So that is input is supposed to be A and B, and use this half adder, and you can obtain its results and its carrier. Okay, if there's no carrier, then carrier is supposed to be 0, right? If it has one carrier, it's supposed to be 1 here. So the results and its carrier. So let's check how does this work. Okay.
First three are 0 plus 0 equals 0.
I'm sorry, let me check. Does I share my voice?
1 plus 0 equals 1, and 0 plus 1 equals 1. Remember that in binary, 1 is the same as true, and 0 is the same as false. So this set of inputs exactly matches the Boolean logic of an XOR gate, and we can use it as our 1-bit adder. But the fourth input combination, 1 plus 1, is a special case. 1 plus 1 is 2, obviously, but there's no 2-digit in binary. So as we talked about last episode, the result is 0, and the 1 is carried to the next column. So the sum is really 1, 0 in binary. Now, the output of our XOR gate is partially correct. 1 plus 1 outputs 0, but we need an extra output wire for that carry bit. The carry bit is only true when the inputs are 1 and 1, because that's the only time when the result is bigger than 1 bit can store. And conveniently, we have a gate for that, an AND gate, which is only true when both inputs are true. So we'll add that to our circuit too. And that's it. This circuit is called a half adder.
Okay, so this is how we accomplish or implement the adder, a half adder in our computer. We use some logic gate to accomplish this task. So we list the results firstly, and then we, according to the results of this addition, we select suitable logic gates to accomplish such kind of tasks. So we have several other logic gates in the computer. Firstly is the XOR logic, what we have used in this half adder, right? And we also have NOT, which one is the inversion. And we also have OR. That is, no matter each input is 1, then you obtain the results is 1. Okay, for example, 0, 1, you can obtain 1. Okay, 1, 0 is also 1. If 1, 1 is also 1. Only all the inputs are 0, you may get a result is 0. So that's the OR logic gates. And the AND logic gates we have already talked about. Only if 2 inputs are 1, you obtain the results of 1. Otherwise, the result is supposed to be 0. Okay, as if there's 1 0, at least 1 0. As if there's a 1 0 as the input, you can obtain the result as 0. So there are several different logic gates we can accomplish by using the logic circuit to create such kind of logic gates by the circuit. And then we use such kind of logic gates, we can accomplish different arithmetic circuit design. Okay, so we can create our ALU chip. So now we can add 1 bit, right? So how about if we have a carrier in the input, right? Because we just consider the situation directly to 2 bit, but in a lot of situations we have a carrier, right? So if we want to accomplish a 2-bit arithmetic, a 2-bit addition with a carrier, we need a 4-adder unit so that we can also get its result and its carrier. So how we accomplish this 4-adder? We can use the half adder created earlier to accomplish this task. Let's check it.
We're going to have to add 3 bits together, not 2. A full adder is a bit more complicated. It takes 3 bits as inputs, A, B and C. So the maximum possible input is 1 plus 1 plus 1, which equals 1 carry out 1. So we still only need 2 output wires, sum and carry. We can build a full adder using half adders. To do this, we use a half adder to add A plus B, just like before, but then feed that result and input C into a second half adder. Lastly, we need an OR gate to check if either one of the carry bits was true. That's it, we just made a full adder.
Okay, so this is how we made a full adder. We use the half adder to make a full adder, okay? And okay, so we've learned about this 1-bit half adder and 1-bit full adder, right? With a carry or with without one carry. Anyway, it's a 1-bit adder. So how about we have 8-bit adder? How could we do this addition to accomplish this task? So you can check.
Let's start with the very first bit of A and B, which we'll call A0 and B0. At this point, there is no carry bit to deal with because this is our first addition. So we can use our half adder to add those two bits together. The output is sum 0. Now we want to add A1 and B1 together. It's possible there was a carry from the previous addition of A0 and B0. So this time we need to use a full adder that also inputs the carry bit. We output this result as sum 1. Then we take any carry from this full adder and run it into the next full adder that handles A2 and B2. And we just keep doing this in a big chain until all 8 bits have been added. Notice how the carry bits ripple forward to each subsequent adder. For this reason, this is called an 8-bit ripple carry adder. Notice how our last full adder has a carry out. If there is a carry into the 9th bit, it means the sum of the two numbers is too large to fit into 8 bits. This is called an overflow.
Okay, so this is how we accomplish 8-bit add addition. And if we have a carrier for the last position, it's supposed to be an overflow. That is, we cannot represent the number within these 8 bits. We have also talked about these concepts in our previous class. So I showed an example here. In fact. Firstly, and the concept about this overflow. If there's a carry into the 9th bit, it means the sum of the two numbers is too large to fit 8 bits. We call it an overflow. So in general, overflow occurs when the result of addition is too large to be presented by the number of the bits you are using. So this can usually cause errors and unexpected behavior in the computer. For example, I showed a very interesting example here is the game, okay? It's a Pac-Man game. I'm not sure how many of you have played this game earlier. So if you played in the last level, the overflow may occur. Let's check this interesting phenomenon.
The original Pac-Man arcade game used 8 bits to keep track of what level you were on. This meant that if you made it past level 255, the largest number storable in 8 bits, to level 256, the ALU overflowed. This caused a bunch of errors and glitches, making the level unbeatable. The bug became a rite of passage for the greatest Pac-Man players.
Okay. So it's a very interesting example of the overflow in this Pac-Man game. If you played this game, you may try to in this last level, and you may find this very interesting situation.
The original Pac-Man.
Okay, so in the ALU, what other arithmetic can we do in the ALU despite this addition? And we can calculate and with a carrier rate. We can also do the subtraction. That means B is subtracted from A. Okay, we can also do the subtraction with a borrow. That B is subtracted from A with the borrow. And we also do this negate. That is, A is subtracted from 0. That is means we flip its sign. Okay, so from the minus to positive, or for the positive to the negative. Okay, just a change or flip its sign. And we can do this increment each time we add 1. Okay, we also do the decreasement each time we subtract 1 from it. Okay, a lot of other subtraction, a lot of other arithmetic operations can be done in this area.